Then I would like to move on because once we get into the more technical aspects, I'm sure there will be lots of questions. So I would like to invite our next speaker, Wim de WAELE from University of Ghent. He will give an overview of the long-term performance of the adhesively hybrid joints.
Okay, good morning. So my name is Wim de WAELE. I come from Ghent University, and together with my colleagues Pankaj and Rahul, also present in the room, we performed quite some tests to evaluate the long-term behavior, long-term performance of these adhesively bonded joints. Within work package 1 of the project, there was, let's say, a balance between experiments and simulations. The simulations will be dealt with in a next presentation by Frans from M2I. But the experimental parts mainly focused on 3 levels of tests. We tested at the material level to characterize material behavior themselves. We tested at joint level, and we tested at component level. Of each of these levels, I would like to give you a little bit of more insight in how it dealt with reaching the goal of evaluating that long-term performance. So looking at the material level, it was performed to, on the one hand, characterize all the constituents of the joints that can help as an input to the simulations, but it also helped us to evaluate the performance of these materials under both unaged and aged conditions. So we looked at both mechanical properties, conventional mechanical testing in tensile shear mode, looking at the interface properties, toughness-related properties. We looked at physical properties like transition temperatures, like moisture uptake. And based on, for example, the moisture uptake, it was found that full saturation in a salt spray chamber was reached after about 6 weeks of exposure, which should correspond to a value of 31 at the graph at the lower left of this presentation. At that time, we reached full saturation. If you look here at that graph, it shows you the tensile strength. You see that there is a small drop in the tensile strength of the MMA adhesive directly from the start, but not further affected by longer exposure. So that remains quite stable. The same was found for tensile modulus. For the ductility of the material, there was no clear influence of the exposure. At the right, what you see after, again, 6 weeks of aging, 35 degrees, 50% relative humidity, we evaluated the fracture toughness of the interface between steel and adhesive. So there is a test specimen with a pre-crack at the top. The test or the specimen is loaded in fatigue, indicated by the red curves, and we tried to monitor the extension of the crack length. The graph in the middle shows you the energy at the bottom, the crack propagation rate at the vertical axis. Both aged and unaged specimens need exactly the same energy to initiate crack extension, and both start or stop at approximately the same critical toughness for final failure. That are the dashed lines that you see on the graph. The red curve indicates that the crack propagation rate at the start of the test at lower toughness values is a little bit larger for the aged specimens, but near the end they reach approximately the same, with the aged ones a little bit slower in further crack propagation near the critical energy rate. So quite comparable, let's say, basic properties with only minor reductions in mechanical behavior. If we go a level higher, we are looking at the structural joints themselves. We are looking here at an idealized joint. It's a double lap shear specimen with an overlap length of 2 × 150 millimeters. It's the black part in the image at the right, painted in black to be able to follow temperature evolution with infrared thermography. At the bottom left, you see a photograph of the tensile test setup, and I just added this to the slide to show you that we try to follow quite a lot of the mechanical behavior. At the left, there are 2 cameras installed for digital image correlation to follow the strains in the adhesive. At the back, there is an infrared thermographic camera to follow the damage evolution. We also had visual inspection and tried to see what happened with damage evolution during the fatigue testing. All tests were performed at 4 Hertz, maximum frequency we can reach to avoid that there would be any self-heating in the adhesive, and as a result, maybe differences in damage evolution. Tests performed at an R ratio of 0.1. And then, for example, at the right, you see an image of the damage evolution taken by 2 infrared thermographic images. At the left one with a lot of green at the start. At the right, very close to the failure, where you see a little bit of hot spots arising at the interface between adhesive and composite. If we look at the properties themselves at the end, so we did quite a lot of series of these fatigue tests, and if I look at the fatigue properties of aged specimens, so again, aged in the salt spray aging, 6 weeks, 35 degrees, 50% relative humidity and 5% of salinity, you see the specimen at the top right, so you see the nice brown oxidized color. So near the transition from the steel to the adhesive, there is a part of the steel left uncoated, unprotected, so that we could have maybe also a little bit of creeping corrosion starting at the interface between adhesive and steel. Specimens were performed, or specimens were subjected to testing at very different stress levels. At the left, I will come back to that image a little bit later, but at the left you see results of static testing, where we reach about in between 6 to 8 megapascal in shear strength in the adhesive. At the right, you see an overview of the fatigue tests. At the horizontal axis, the number of cycles that were survived for a certain maximum shear stress at the vertical axis. So the blue full circles indicate failures where the specimens really reached rupture. At the bottom, near the horizontal dashed line and a little bit above, you see a few circles which are open and with an arrow to the right. These indicate specimens that did not fail at all. So we reached 5 million cycles of fatigue without failure. It must be said that at the specimen at 1 megapascal, we could not even see any damage at the adhesive. For the specimens tested at 2 megapascal, 2.5, we could see minor small hackles, small cracks in the adhesive, but without any significant influence on the mechanical behavior. So there are quite a lot of repeat tests, so this is repeatable behavior. Final rupture of the specimens was always introduced as failure at the composite plates themselves near the interface with the adhesive, so interfacial damage or delamination. All the tests that survived the fatigue were afterwards also tested up to static strength to evaluate if fatigue had any influence on the remaining strength. And that's what you see at the bottom left. The full lines are tests without fatigue. The dashed lines are quasi-static tests on specimens that had been fatigued up to 5 million cycles. And you don't see any, you could maybe think is a little bit higher, but we analyzed this from a statistical point of view, and there is no significant difference in tensile strength between fatigue-tested specimens or quasi-statically tested specimens. So that means that for these stress levels at 1 megapascal, 2 megapascal, 2.5 megapascal, there is no real influence on fatigue on the adhesive behavior. So then we have to transition to a component level, to joints that are representative for joints in the real scale. At the right of the slide, you see on the one hand the damen joint, the darkest colors and thick composite panel or sandwich panel of composite plates on balsa core with steel brackets. On the right, you have the BAE specimen with a very thin adhesive layer of vinyl ester. So this presentation focuses on all the results of the damen joint with the MMA, very ductile adhesive, where we have a specimen at the right of, let's say, approximately 950 millimeters, 95 centimeters. The steel bracket, I think, about 100 or 10 centimeters high, and the adhesive in between 6 and 10 millimeters of thickness. All specimens were manufactured in shipyard conditions, and we had tests in pure tensile mode, bending mode, and at the center, I'll come back to that, is what we call an Archon type of test, where we do loading, which is under an angle to the specimen, to have multi-axial loading in the specimen. These specimens are now too large to be put into an environmental chamber for salt spray aging. So we had to develop an aging protocol that was able to mimic the same conditions. That aging protocol has been designed based on full immersion in salt water at the higher degrees of temperature. So Linda already initiated in her presentation some background on the calculations that were performed. The ambition of this protocol is to really mimic the same types of degradation mechanisms, which consists of, on the one hand, moisture uptake, moisture diffusion throughout the adhesive, and on the other hand, also potential creeping corrosion at the interface between adhesive and steel. So that were the two degradation mechanisms that we were aiming at. And besides that, we wanted to be able to replicate an operational condition of 5 years of exposure to 35 degrees Celsius and 50% relative humidity. 5 years, we have already spoken about 25 years of total life, but 5 years should be the lifetime in between two dockings of the ships at which always complete inspection, repainting can start. So this should be the time that lasts without any potential knowledge about corrosion damage. So based on the calculations that Linda introduced, we found out that the best approach to mimic this is, on the one hand, what you see at the bottom photograph at the left, is to take away 15 millimeters of adhesive, and on top of that, to put this component into a saltwater bath, 3.5% salt water content, or 3.5% salt content in the water, at a higher temperature, 50 degrees Celsius, and 10 weeks of full immersion. That should allow, on the one hand, the diffusion of your moisture inside the composite, inside the adhesive, At the same time, we applied some scriber lines, also introduced by Linda, at the interface between adhesive and steel to allow potential creeping corrosion. So for that reason, to allow this to be done on these very large specimens, we had to design a saltwater immersion bath. You see a few of the dimensions around here. Let's say a little bit more than around 1.5 cubic meters of content. The setup is fully controlled to have a stable temperature at 50 plus or minus 0.5 degrees Celsius. Salinity is controlled. You see some tubes for continuous recirculation of water so that we have very homogeneous saltwater content, but also very homogeneous temperature at all locations of the specimens. And at the right, you see that we are able to put, for example, 4 Arcan specimens, very large specimens, but together with also the tensile specimens in that bath, and to be able to reduce the total testing time, because we are dealing with 10 weeks before in immersion before we can start the testing. Testing is done in fatigue. So Luc already introduced part of this diagram. So from Bureau Veritas, we got a load histogram representative for 25 years of operation of the ship, stress levels reached at the joint. If you look at the numbers on the graph on the vertical axis, you see that stress levels in fatigue range up to around 2 megapascal. And the number of cycles that are indicated at the bottom are 10 times more than what the ship sees in reality. So there's a safety factor of 10 on the number of cycles. Of course, we were already dealing with 25 years times 10. We have to reduce the spectrum for laboratory testing. So the first thing that we did was remove these cycles that we are quite sure of that they are non-damaging. I had shown you a limit of 1 megapascal of shear stress in the joint specimens. We again applied a safety factor. We divided the 1 megapascal by 2, and everything below 0.5 megapascal has been erased. That's the non-damaging part. And for the rest of the spectrum, we divided all the blue boxes in a lesser amount of orange boxes. So in that red frame, for example, you see that all the blue boxes, all the cycles are added to the highest level of stress, again, to be conservative. So in that way, we binned the load schemes and we tested the joint now at 4 Hertz. That means that 25 years of operation, a safety factor of 10, could be reduced to a testing time, if we would test 24 hours a day, of 10 to 11 days. All the joints that have been fatigue tested, I show you here the tensile tests, survived completely the fatigue loading. So if you see a broken specimen at the right, that's because we did a residual tensile test at the end. There was no fatigue damage, not visible in the load signals, not visible from a visual point of view by inspection. So there was no damage at all. At the end, we did the residual tensile strength. And what you see on the graph at the bottom left is a collection of tensile tests where we have a combined AF, means that it was aged without the A. The FS, that is the highest line, is the unaged part. F plus T means fatigue tested plus tensile tested. T would mean only tensile tested. But if you look at all these graphs, you see that the evolution of load versus elongation or displacement is always the same, and the final strength is again not different for aged, unaged, fatigue tested or non-fatigue tested specimens. So we have quite reproducible strengths. And finally, if you look at the failure condition at the right, you see a crack at the interface between the composite and the adhesive, but the failure really started within the composite itself. That's why I added that photograph. So there is delamination within the composite that then, after very dynamic rupture, transferred to an interfacial or an interface failure in between adhesive and composite. The Arcan loads or the Arcan tests, you see at the right how the specimen fails in a static test. So we did quite a lot of these tests again, but all tests, again, aged and unaged tests in the static load reached again the same level of strength, and again damage always started, maybe you have seen it on the short movie at the right, but the damage really started at the top right there in the composite, again delamination, and then transferred through the composite, and afterwards led to some failure at the interface. This specimen was designed in such a way that it corresponds in loading to the loading conditions that is at the fore-aft of the ship structure. Also, that small simulation at the top you might have seen in the presentation of Luc. So to conclude this presentation, I can summarize that we have investigated the long performance or the long-term performance of the adhesive joints by testing at multiple levels. Fatigue limits, stress-life relationships have been established after salt spray aging at idealized joints. For the large components, we designed a saltwater immersion bath to mimic the exposure to operational conditions. We designed a laboratory load histogram for accelerated laboratory fatigue testing, and all the large-scale joints were surviving, I would say, the long-term exposure to end environmental conditions and mechanical conditions without any damage in the adhesive. The final failure of these BAE types of joints were initiated by delamination within the composite. And that concludes my presentation. Thanks.
Thank you very much. Yes. Do we have any questions from the floor or online, maybe? Yes, please. Could you walk to the microphone, please?
Thank you for this presentation. Very impressive testing, and I think very good results for the result that for the joint Dame proposed here in this project. I was wondering for the large-scale component testing, and maybe it's a topic that will be addressed later in today. But did you also apply the structural health monitoring equipment or test methods on those tests?
Yes, I cannot go back, but on the image of the large-scale Arcan test that you saw, there were a lot of sensor lines from Common Sense installed. So I don't know if that will be part of your presentation, but you see there in the mid-image, you see these yellow lines. So both on the steel and on the composite, we had a lot of sensors installed. Also on some small-scale tensile tests, but I think this is probably the most impressive one.
Okay, I'm curious about that presentation then, because you showed that there was not very much damage accumulation and after the fatigue testing, I think, because the...
Not in the adhesive, no. Yeah.
No, indeed, yeah. So we'll see later then what has been measured and how this was performed. Okay, thanks.
Thank you. Yes? please.
Good morning, everyone. My name is André Vaders. I'm part of the Defense Material Organization in the Netherlands. I would like to take the opportunity to at least thank Professor de Waal and everyone involved in this research, because as we see it for now, it gives good results. I do see results where not the adhesive is failing, but the composite itself. So that is what we like to see for the future. Further, I would like to add on and take this opportunity to also state something about the application. Where do we do this research for? We do this for future applications. I gave a small presentation in an earlier workshop in Qualify and announced that the weight problems of future frigates will be a large challenge. And indeed, it appeared a large challenge. And so in the end, the project in the Netherlands, new frigate build, accepted that superstructure, composite superstructure with adhesives is applied for the future frigate. And this is in development. And that acceptance of this composite superstructures is also thanks to the research done up to now in all the aspects of also the adhesive joints connected with the steel hull. So I would like to thank you all and keep up the good work. And there is good work coming up. One part of the good work coming up is that there is an initiative by the German and Netherlands government to initiate an EDF fund, and those are very large funds, aiming at bonded joints in the future. And I would like to call everyone up to be informed about this EDF proposal and opportunity, and to team up and come up with a maritime application case. Up till now, it's only Air Force, but I would like to see it also in a Navy case. And that goes to my conclusion, and that's an announcement of this fall 2022. There will be a new NATO working group on composite joints and the quality control of composite joints. I would like to ask a presenter to present the findings of Qualify within this NATO working group in the fall of this year. And I already heard about one volunteer, but please come to me if you would like to present something in that forum. And then several NATO countries will be informed of all the results. Thank you very much, and keep up the good work.
Thank you. That's very great to hear. We are looking for funding for a follow-up Qualify project, so that's great. Thank you. Are there other? Yes? Yes, please.
Yes, so Luc Mouton from Bureau Veritas. It's difficult to ask a question after such announcement, as I think not much of what I say could be sound really interesting. Thank you. I just want to note that in 2019, when we had done one of the Qualify meetings, we had one of the people in the room who asked us about this test that we were thinking of, making 5 to 7 weeks, we didn't know yet at that time, immersion test of the full-scale specimen, and at 50 degrees. And the person said, but the problem is that your test is too severe, and you should plan something in case it fails, and so that you can, what kind of conclusion can you withdraw if the test fails? And I think now we are 2 years later, the test has been performed as we planned in this time. So 5 weeks or 7 weeks at 50 degrees, immersed in the water, and then it came out. Specimens came out, were tested in fatigue, and the strength was full. The result strength was fully assured. So I think it's thank you for this person who we will send him the results and tell him about the results. It's nice to see it.
Look, we are losing you. The last part.
Yeah, so last part, just that it's nice to see 2 years later the achievement has been done. And it seems that this joint is really strong and tough, and the test that we have set up in place show that we are really stringent in the end.
Sorry, we couldn't hear, but I understand that you're happy to see that the aging test at 50 degrees for 10 weeks were successful, and it wasn't an aggressive aging protocol.
It was an aggressive aging protocol.
I mean, it didn't destroy the joint in that sense,
Yes.
because that's what initially was assumed, that this could be too aggressive, but it proves that it's not.
Exactly.
Okay, great. Thank you.
Thank you.
Thank you, Wim, very much.
Yep.